presenter is Pablo de Caria from Argentina, and it's for me a pleasure because I was thinking and I asked to Isidoro if probably it's the first time that people from Argentina stay here, and I am Flavia, obviously, and I am very happy because we have a lot of relation, a group of Mexico have a lot of relation with Argentina now, and really it's a pleasure introduce to Pablo here. Thank you very much.
Well, I also wanted to express my gratitude for the invitation and for giving me the opportunity to be in Mexico for the first time. Well, I am going to speak about clique graphs, iterated clique graphs, the clique operator, and the powers of the clique operator, and octahedral graphs. So, first of all, I would like to briefly see what each concept means. So, a clique is a maximal set of pairwise adjacent vertices of a graph. The clique graph of a graph G is a graph whose vertices are the cliques of G, and two of those cliques are adjacent when their intersection is not empty. The clique operator is the function which assigns to each graph its clique graph K of G, and the power K to the n is the composition of the clique operator with itself n times. Well, when we have a graph G, the image under K to the n of G is called the nth iterative clique graph of G. So if we use this symbol to denote the family of all graphs, K of G is the class of clique graphs, K squared of G is the class of second iterative clique graphs, and so on. This presentation is motivated by the interest in knowing what graphs are in each class. For clique graphs, we have a classical theorem by Roberts and Spencer that say that a graph G is a clique graph if and only if there exists a Helly family of complete sets of G which cover the edges of G. What does this mean? Complete means that there are sets of mutually adjacent vertices, and the family is Helly when pairwise intersecting members of that family have a common element. The characterization we have shown here is one of the few tools we have to prove that a graph is not a clique graph. This is the simplest example of a graph which is not a clique graph. And to see that this is not a clique graph, we can assume that there is a cover like the one of the theorem, a cover by completes that is Helly. And in that case, we should need to have the triangle 1, 2, 3 in that family, because otherwise, to cover the edges of that triangle, we should have each edge separately. But the problem of having each edge separately is that the Helly property is not satisfied. So we need this triangle, and similarly we need this triangle, and again we have problems with the Helly property. So this confirms that this is not a clique graph. Well, having this characterization of clique graphs doesn't mean that it is easy to identify clique graphs. Actually, the problem of recognizing clique graphs is empty complete. Recognizing when a graph is in K squared of G is even more difficult because of that. So it was so difficult that it was even unknown whether K of G and K squared of G were the same thing. That was an open problem for at least 10 years. And the main goal of this presentation is to show that those classes are not equal. To prove that, it is useful to take into account that a graph is in K squared of G if and only K of G intersection the pre-image of G under the clique operator is not empty. An idea of that fact is given by this picture. So if we want to try to find a graph in K of G minus K squared of G now, we have to take into account that it cannot be the clique graph of a graph whose cliques form a Heli family, because clique-Heli graphs are clique graphs. So we could start with this graph that is not clique-Heli and try to expect that its clique graph is the graph we are looking for. But the clique graph of this graph is very simple. It is the complete graph on 4 vertices, and it is almost immediate that it is not the graph we are looking for. But adding 3 edges to this graph produces a considerable change. We obtain a graph that is called the octahedral because of the simple fact that it represents an embedding of the octahedron on the plane. And this graph can also be seen as 3 pairs of opposite vertices, where opposite vertices like this and this are vertices that are not adjacent, but they are adjacent to all other vertices of the graph. And for that reason, we are going to call this graph O3 also. We are using primes to indicate when vertices are opposite. The clique graph of this graph is can also be seen as pair of opposite vertices, this, and that's why we call it O4. Many people suspected that this graph O4 was the graph that was in K of G minus K squared of G, but, well, it wasn't possible to prove it before, and now I would like to tell you how that can be proved. All what we need to see is that any graph whose clique graph is O4 is not a clique graph. Well, that means that we can start by trying to find the family K-1 of O4 of graphs whose clique graphs are O4. To find K-1 of a graph, we need this property that says that K-1 of graph G consists of the intersection graphs of Heli and separating families of completes that also cover the edges. It is very similar to the characterization of clique graphs, but we have an additional condition that the family has to be separating, and separating means that for every 2 vertices, X and Y, there exists a member of the family that has X but doesn't have Y. For example, for this graph, this is a Heli family. These sets are complete in the graph, and they cover all the edges of the graph. But it is not a separating family, but obtaining separating family is easy by adding unit sets. So we have all the conditions of this theorem now, and when we compute the intersection graph of this family, we obtain a graph whose clique graph is just this. Well, that being said, we can prove that any graph whose clique graph equals O4 has O3 as an induced subgraph. An idea of the proof is the following. We use the theorem of the previous slide, so we can take a family F that is Heli, that is separating, that the members of the family are complete, and that all the edges of O4 are covered, and, well, the intersection graph of this family has to be G. Now we will have to take a minimum family of F that also covers all the edges of O4. It is even possible that F prime and F are the same families. For this family F prime, we can prove that the cardinality of each member of this family equals 4, that the intersection of any 2 members of F prime is even, and that if we have a set F in the family F primes, then we must also have the set of all opposite vertices of the vertices of F. With all these conditions, it is guaranteed that we can choose 3 intersecting members, F1, F2, and F3 of F prime, and together with the opposites, we can obtain O3 as an induced subgraph of the intersection graph of F, which is just the graph G. So it is already proven that O3 is an induced subgraph of G. Now, now that we know that O3 has to be an induced subgraph of G, we will take a set B prime just inducing O3, and for each of the triangles of O3, we will consider a clique of the general graph that contains that triangle. That way we will obtain 8 cliques because of the structure of this graph. All the cliques containing different triangles are also different. And since O4 is the clique graph of G and O4 has 8 vertices, that means that all the cliques that we obtain by the procedure described before are just all the cliques of G. So, for example, this graph would not be in K-1 of O4 because this vertex is not adjacent to all the vertices of any triangle of the induced O3, so it is impossible to put this vertex in any of the cliques that I have described before. But that could be fixed if I add this edge. Now this vertex is in the clique that contains this triangle. So this is a possible additional set for vertex for any graph on K-1 of O4. We can also have vertices that are adjacent to all the vertices of 2 triangles that share a side. We can also have vertices that are adjacent to all the vertices of the induced O3 except one vertex. But that's not all, because, for example, if we make some changes on the incident edges on this vertex, now there is a problem. That problem consists in the fact that for this triangle, I have 2 cliques containing that triangle. This clique and this clique. So to keep having 1 clique per triangle, we'll have to make those 2 vertices adjacent, and now this graph is in K-1 of O4. Well, this gives us an idea of the structure of the graphs in K-1 of O4. And with those structural properties, we can prove that if B prime is still a set inducing O3, then no vertex of G is adjacent to all the vertices of B prime, that if 2 vertices have the same neighbors in B prime, then they have the same neighbors in the general graph. That means that the 2 vertices are twin, and that if U and B are two adjacent vertices, W is a vertex of B prime, then U and B have to be both adjacent to W or the opposite vertex of W. Now that we know what the graphs of K-1 of O4, we can try to prove that none of those graphs are clique graphs, and that would complete the proof that O4 is a graph in K of G minus K squared of G. So we will try to assume that on the contrary there exists a graph G in K-1 of O4 that is a clique graph. So in that case, by the characterization of clique graphs, we will be able to take a hairy edge cover F of complete sets, and because G is a graph in K-1 of O4, we know that there is also a set B prime of vertices inducing O3. In this context, we will define for each triangle X, Y, and Z of the induced O3 vertex B sub X, Y, Z that must have in each member of F containing XY, XZ, or YZ. This vertex always exists because the family is being assumed to be Heli. These 2 vertices happen to be adjacent, when their indexes share two common vertices. For example, the vertices B sub ABC and the vertex B sub ABC prime are neighbors because both are, by definition, in each member of F that contains the set AB. And since the members of F are complete sets, any two vertices inside a member have to be adjacent. We have to define one more thing. We will define the family C of Fb prime that consists of the triangles of the induced O3 that are contained in at least one member of the helicover of the edges of the graph G. For example, we have this family will consist of the triangle ABC, which is here, of the triangle A prime BC, which is also here, and the triangle A prime, B prime, and C prime, which is here. Some of the properties of the vertices that I have just defined are that by definition it is simple to see that they are adjacent to all the vertices of the index. If there is a triangle in C of F prime that contains two vertices of the index, then the third vertex of the triangle has also to be adjacent to this vertex, because when we take a member of the family F containing this triangle, then by definition, because of these two vertices, this vertex is also in that member, and since all the vertices there are adjacent, we immediately conclude that these and these are adjacent. Well, depending on the triangles C of F prime have and their relative positions, we have many possibilities for what C of F prime can be. It can be empty if it has no triangle. We will call it a triangle. If it has just one triangle, we will call it a rhombus. If it has two triangles that share a side, a bow if it has two triangles that only share a vertex, and so on. In this context, we can see that C of Fb prime cannot be castle. A castle was one of the cases in the previous slide. It is defined as three triangles that always intersect at a single vertex. In that case, we would have, if C of F prime contained this castle, it would happen that the vertex B A prime BC, because of the reasonings of the previous slides, will be adjacent to all the vertices of B prime, and I had mentioned before that no vertex can be adjacent to all the vertices of B prime. So it cannot be a castle. Another case is the case of an umbrella. An umbrella is defined as two triangles that don't share vertices, plus a third triangle that can occupy any position. If we have an umbrella like this in C of F prime, then we can see that this vertex B sub A B prime C has the same vertices in B prime as C, so they have the same neighborhood by one of the properties I mentioned before. And on the other hand, if we now consider the vertex B sub A B prime C prime, we can find immediately four vertices for it. Since it is adjacent to B sub A B prime C because they share two vertices in the index, that fact adds also C as a neighbor of this. And adding C, now we have that this vertex has the same neighbors in B prime as B prime. Well, the proof continues by trying to identify twin vertices. Always the reasons are the same, until we get that there are two adjacent vertices. that have the same neighbors that as opposite vertices. That is something impossible. If two vertices are adjacent, these two vertices should also be adjacent, and this is a contradiction. So C of f prime cannot be an umbrella, or cannot contain an umbrella either. Well, all the remaining cases are not as direct as the one I have covered before, but we continue to try to find twin vertices. So for a case of a round that is the set of all triangles around a vertex, for a round like this in C of f prime, we must have that this vertex or this vertex has the same neighbors as A prime, but as it is not as simple as the previous cases, we have to use new arguments now. So suppose that this is the correct case. In that case, we will define a set B prime by taking A prime out of B prime and replacing it by this vertex that has the same neighbors as A prime. This will ensure that the graph induced by B prime is also O3, but there could be a change in C of f B prime. In this case, we have a round, and for this configuration, we will have an umbrella. We could even have more triangles, but the simple fact that we have an umbrella here means that this is a contradiction, because we have already seen that umbrellas are not possible. Well, the proof has many cases, and we continue by discarding cases. We have already seen that 3 cases are impossible. It finishes when we see that all cases are impossible, and this diagram shows how each case is proved depending on the other cases. So if this family cannot equal anything else, that means that we arrive at a contradiction. We have supposed that there was a graph such that k squared of that graph equal 04, and well, all this reasoning show that it is not possible. So we are now sure that 04 is the graph in k of g minus k squared of g. Now, it would be interesting to be more general and wonder whether k f of g is equal to k n plus 1 of g or not. Well, here they should be exponents. It's a mistake. It would be great if they are different, and if that would be true, it would be reasonable to think that the graphs that separate those classes are similar to O3 and O4. So we will define for m larger than or equal to 3 the n octahedral graph also O sub n as a graph that has 2 times n vertices, and like here, where the only missing edges are I prime. This class of graphs has 2 to the n cliques, because each clique can be obtained as a selection of one vertex per each of these sets, and for each of the cliques that are obtained that way, there is one other clique, one unique clique that do not intersect that clique we were considering. For example, the only clique that does not intersect 1, 2 until n is 1 prime, 2 prime, n prime. And this allows to prove that the clique graph of O sub n is also another octahedral graph. More precisely, it is O sub 2 to the power of m minus 1. Let's start with the simplest case, the case where n equals 2. Well, if the clique graph of O3 that was O4 was a case of a graph in k of g minus k squared of g, one could think that it is possible that k squared of O3 that equals O sub 8 is a graph in k squared of g minus k cubed of g. Here there should be exponents too. One good way to try to start to prove that is that for any graph G whose graph equals O8, O4 has to be an induced subgraph of G. And the proof is very similar to when we have proved that for any graph whose graph equals O4, O3 is an induced subgraph. We also take a family F that is minimum heavy and covering all the edges, and we see that the cardinality of every member of that family equals 8, and that for any two members of that family, the cardinality of the intersection equals 0, 4, or 8 for all couple of members. That means that if we have a set B prime inducing O4 in this graph G, whose big graph is O8, we can have additional vertex that at least must be adjacent to all the vertices of one clique of O4, and it is also possible that that vertex is adjacent to up to 3 more vertices, but not to all the vertices of B prime. And these additional vertices are adjacent when the intersection of the neighborhoods contain the clique of reduced O4. Well, so we have an idea of the structures of the graph in k-1 of O8, and now the question would be if any of those graphs are in k squared of g. If they are not, then O8 is effectively a graph in k squared of g minus k cubed of g. Well, there are two. Okay. Well, we don't have a proof that all these graphs are in k squared of g are not in k squared of g, but it would be interesting to consider some examples of graphs in k-1 of O8. For example, for these two graphs, we can see that some graphs whose graph are equal to them are very similar in structures to graphs that were in k-1 of O4. In case that all the graphs in the tree image of these graphs were similar to O3, then it would be simple to prove that these graphs are not in k squared of g. But we don't know that. To make things worse, there are cases of graphs in k-1 of O8 that are not even clique graphs. For example, a graph that is obtained from O4 by adding 8 simplicial vertices whose open neighborhoods are these cliques of O4. And the reason why this is not a clique graph is in this last example, because when we consider this clique, which is the neighborhood of this vertex, let's suppose that this clique of O4 corresponds to this round, then to generate this vertex in the clique graph, it is just necessary to add this edge and this new vertex. But if this corresponds to a round, then this neighborhood of this other vertex will correspond to a Castle set, and to make things work and generate this vertex in the clique graph, a more complicated structure is needed. it is here in the center. But that's not the only case for cliques of O4. We have already seen that some cliques of O4 correspond to rounds here, some corresponds to castles, but there are even cases where more strange. For example, this. There are 4 triangles that intersect each other in a pairwise way. So why we have these 8 vertices, these 8 neighborhoods? The reason is that when we have these 8 neighborhoods, we ensure that one of the cliques of O4 should correspond to at least one clique of this form. That means that there will be no graph similar to O3 in the pre-image by the clique operator, and well, it can also be deduced by some other reasons that there are not any other graph in the pre-image, no other structural graph that allows this graph to be a clique graph. Well, this is just to show that it could be difficult to prove that the graphs of k-1 of 08 are in k squared of g or not, that the proof could require too many cases. Finally, I would like to leave some questions for the general case, any value n, not necessarily 2. Well, the question is it true that F is a mini-unitary family of complete sets covering all the edges of O sub n? Then the cardinality of each member of F equals n, and the intersection of every 2 members equals 0, the half of n or n. If that would be true, there is an argument that would allow to prove that the graphs of these 4 are the only octahedral graphs that are clique graphs. And in that case, it can also be proven that O sub n plus 1 would be an induced subgraph of this graph, and well, that could be hopefully the beginning for a general proof that k to the n of g is different to k to the n plus 1 of g. Well, thank you.
Do you have a short question?
So when are you going to prove that?
I don't know. Sometimes time is not enough. But well, if things were very good, if I am fortunate, I would say 1-2 years, but who knows?
Okay. Thank you, Pablo. And thank you.